Hello students, today we're going to be talking about congruency in triangles. To begin with, we have been looking at congruency within angles and in sides, but now we're going to be focusing in on two or more figures. The way that we can tell that two things are congruent would be based upon their size and their shape. So we're looking for that the angles and all the lengths are all congruent. So if you can see the figure on the left there, we have the same size and shape. Theoretically, those angles should be the same and the sides are the same, while the ones on the right are clearly not congruent. They have two different or three different sizes, even though they're all triangles. So incongruent figures, all the parts of one figure, are congruent to the corresponding parts of the other figure. Incongruent polygons, this means that the corresponding sides and corresponding angles are congruent. So we talked about corresponding angles in the past. Those are the things that are in the same position. So angle A and angle F are in the same position, so they're corresponding. We can list those corresponding sides and angles and showing that they are congruent. So for example, angles A and F are congruent. Angles B and E are congruent, and angles C and D are congruent. And you can tell from the picture based upon the markings in there. So we have one arch, two arches, and three arches. We can do the exact same thing, but with corresponding sides. So segment AB and FB are the same, segments BC, ED, and so on and so forth. Now the most important thing here is being able to write your congruent statement. Our congruent statement is a direct comparison between the two triangles, or if it's four-sided, is the quadrilateral. So for this one here, we have two ways. We have more than two ways, but these are just two of the ways that we can write our congruent statement. So the big thing here is first to name a triangle, we use the symbol of a triangle. So we have triangle ABC is congruent to triangle FED. The order is going to matter. A and F have to be in the same position, B and E have to be in the same position, and C and D have to be the same position in our congruent statement, because A and F are congruent and so are BE and CD. So if we were to rearrange it in a different order, such as BCA, I then have to take the other three and rearrange them as well. So let's take a look at an example using the exact same idea. If we have two triangles here, such as the one on the right, if I want to write a congruent statement, I have to pay attention to where the different angles are. So if I want to start with, say, JKL, I have to correspond the angles to match up. So if J had three arches, if I look at my triangle on the right, T is the one that has three arches. If I said K was next, then I have to say S was next, and if I say L, then I say R. Okay, so this would be triangle JKL is congruent to triangle TSR. Again, those angles have to match up. From there, you can identify the congruent sides and the congruent angles. For corresponding angles, JT, KS, and LR are congruent to each other. And the corresponding sides would be JK, T with TS, KL with SR, LJ with RT. Again, you can identify these pieces directly from the picture here based upon how many tick marks they have or how many arches, or you could pull that information right from the congruent statement. Since they're in the same positioning, J and T would be congruent. If you're looking at segments, it would be JK with TS. And that's how you can use the congruent statement to identify those pieces. So if we were to actually use it to solve some problems here, we have this diagram on the right. We want to solve for X and Y. What we're going to want to do is solve for X first. Now when we do this, we have to make sure that something states that these two things are congruent to each other, and that's what's here in the directions, that DEFG is congruent to SPQR. And now as we move forward, I'm looking at, all right, well, X has to be solved for first because this one has a Y in it, and I'm looking at QR. Well, back on my congruent statement, I see that QR and FG are in the same positioning, so I know that those two pieces are congruent to each other. Well, now I'm going to go ahead and say, well, since they're congruent, I know that the two pieces are equal. And then since they're equal, I can substitute them with their expressions. FG is 12, and QR is 2x minus 4. And then from there, it's just using algebra to solve for x. So I'm going to add 4 to both sides, and I'm going to divide by 2. Moving on, I'm going to now find the value of y. So what I know here is angles F and Q are congruent. Again, if you couldn't identify that from the picture, since it's oriented differently, you could always look here at F and Q are in the same positioning. So I know that angles F and Q are congruent. That means their measures are equal. So once again, I'm going to take the 68 degrees, because that's the measure of F, and I'm going to set that equal to 6y plus x. Well, since this is the same problem, we already know what x is equal to, so I can substitute that in for 8. From there, once again, it's just algebra, so I'm going to move the 8 and divide by 6, and I get my y values equal to 10. Moving on, we have another theorem here. It's called the third angles theorem. What this states is if two angles of one triangle are congruent to two angles of another triangle, then the third angles are also congruent. So this kind of seems like why do we need to have this theorem here? And it's for more complicated problems. But if you take a look at what it means, if this angle here was 70 degrees and this angle here was 30 degrees, angle C has to be 80 degrees to add up to 180. Well, if these two angles are congruent to these two angles, which is what the theorem says, well then this is also 70 and 30, meaning this is also 80. So what this theorem is saying is that if we know 2 out of the 3, we can automatically know that the third angle is also congruent to each other. So here's an example using that theorem. We're trying to find the measure of angle BDC. That's this obtuse angle right here on the side. What we know here is that we have two triangles, ADC and BDC, and they have two angles that are congruent. So in a triangle ADC, which is the one on the left here, we know that two angles are 45 and 30. Now, since we have the markings here, I know in triangle BDC that this measurement is 30 degrees and that this measurement has to be 45 degrees. And that's kind of what I'm basing everything off of. So what I know is that the measure of ACD and BDC are the same, so I can solve for angle ACD first, and I can transfer it over to angle BDC. Or you can substitute the values in for the two angles of the second triangle on the right. Regardless, if I were to start solving for that third angle, I can add 45 and 30 and subtract it from 180, and I know that the measure of ACD, which is this angle on the left here of the triangle, is 105 degrees. Well, since the two angles are equal to each other, that is also equal to 105 degrees. We can also do it in different ways. Some ways that might be helpful, since these triangles are overlapping, may be to separate the two triangles. That's just a piece of advice. One last thing I wanted to go over with you is the reflexive, symmetric, and transitive properties are applicable to our congruent triangles. The first one says that a triangle is congruent to itself. The second one allows us to rewrite the congruent statement in either way. And the third is the transitive, where if one triangle is congruent to another, that same one's congruent to a third triangle, then we can drop the middleman and we can go right from the first to the third. That's all for today. If you have any questions still, please make sure you're asking them in class. I'll see you later.